Number 27 is asking us to find the area of this region in two different ways, once with respect to x and once with respect to y. And I kind of had a feeling, guys, that just like the problem we did in our notes, they're trying to prove a point here, but let's see where we're at. So x is equal to 9 minus y squared. What I'm hoping you guys recognize is the fact that one variable is squared, the other is not. It's to the first power. That makes it a parabola. It's the opposite of what we normally think, where it would be y equals x squared. That means this is a sideways parabola, opening either left or right. And since the y squared has a negative coefficient, it opens in the negative x direction, which is left, so this parabola is probably going to look something like this. And this value here of 9, that's our x-intercept. So I went ahead and started this graph there. There we go. So we've got a graph that's going to look like this. Its vertex will be at the point 9, 0, and it'll do that on top, and it'll do that on bottom. And yet again, my sideways parabolas look nicer than my real parabolas. Anyway, here we go. X equals 5 then is a vertical line with an x-intercept of 5. So there we go, guys. And that cuts off one bounded region of finite area, and that's what they want us to come up with the area for. So again, they wanted us to do this problem in two different ways. So we're going to do it once with respect to x and once with respect to y, and I'll see if I can cram both of these in here in a reasonable amount of space and see if we can get this to work out. Okay, if we're going to run this thing with respect to x, something weird happens. When I go to draw a rectangle here, and this actually would be true for any rectangle that I draw, it is bordered on the top by the parabola, right over here, the sideways parabola, but it's also bordered by the same sideways parabola on the bottom. Now that's a little bit weird. Now what I probably would do is be crafty and just do the area of this shaded portion there and then double it. But I'm going to go ahead and do this a slightly different way here because I want you guys to see what's going on. If we're going to integrate this with respect to x, I already know that my setup looks like this. Area is a definite integral taken with respect to x. And that means that the entire integrand needs to be expressed in terms of, you guessed it, x. Well, this equation right here, guys, is obviously solved for x, but in terms of y. So let's take a little time right here. Let's solve this equation right here for y in terms of x. I'd bring the y squared to the other side and get y squared. I'd bring the x to the other side and get 9 minus x. Then I would take the square root of both sides and get y is equal to plus or minus the square root of 9 minus x. Now that is actually, you guys, two different functions. And the upper function, the top half of this sideways parabola, is the positive case. Y equals the square root of 9 minus x. The positive square root, I should say. Down on the bottom is the negative case. Y equals the opposite of the square root of 9 minus x. So, when I ask you guys the question, what borders this red rectangle right here on the top, it's this curve, minus what borders it on the bottom, that's this curve. So, you're going to see where this is going, guys. This is going to be the square root of 9 minus x minus the opposite of the square root of 9 minus x. Minus negative, of course, just becomes a plus the square root of 9 minus x. And that's what your integrand would look like. And I think you know what I'm going to do with that right away on the next step. Now, before I go any further, let's talk limits of integration. Lowest and highest values of x. So as I scan this region from left to right, it begins right here, or I should really say right here, at x equals 5, and it ends right here at x equals 9. So those would be my limits of integration. Now, as I go to do this here, guys, obviously, I think you all see it, those two terms are identical, so this is going to become the integral of 2 times the square root of 9 minus x taken with respect to x from 5 to 9. And if we wanted, we could pull that 2 out in front with the constant multiple rule. Now, I would do that if I were going to evaluate this integral by hand, which actually isn't that bad. So I'm going to go ahead and do it here. Give me a second. I should have done this ahead of time. Let me reorient my page here a little bit. Okay, so I would probably now rewrite this one last time as 2 times an integral from 5 to 9 of 9 minus x to the 1/2 power taken with respect to x. So where's this going to get us? We've got a 2. The base of our exponent is going to stay the same, 9 minus x. We raise our exponent by 1, that's 3/2, divide by that new exponent, which means multiply by its reciprocal, so that's going to be 2/3. And then lastly, we have to reverse the chain rule by dividing by the derivative within. And the derivative within of 9 minus x is -1. Guys, I can only reverse the power rule here because the derivative within is a constant. So dividing by -1 will just put a negative in front of that whole thing. Now that's weird because it makes it seem like I'm about to get a negative answer, but I think this is going to work itself out at the end. I'll put a bracket right here and a 5 and a 9, and let's see where this takes us. The -2 times 2/3 is a -4/3, and I'll start a big set of brackets now. Let's put the 9 in there. 9 minus 9 is obviously 0. 0 to the 3/2 power is 0. That wasn't bad. Minus, let's put that 5 in there. 9 minus 5 is 4, and 4 to the 3/2 power, I'll just remind everybody, 4 to the 3/2 power means the square root of 4 cubed, which is 2 cubed, which is going to be 8. So I was worried about this negative coefficient out in front, but as I thought, the inner part becomes negative as well. So -4/3 times -8 is going to end up getting us a positive 32/3 square units. And that's the answer we came up with now if we integrated with respect to x. Okay, now they wanted us to do the entire problem again a second way. We're going to do this one with respect to y. So let me shift colors on you here, guys. I'm going to go green with this one. And let's think about what this is going to look like if we start running our rectangles here horizontally. So there's one that I'm going to draw. Here's a second one. Here's a third one right here. So now we're going to take our area as a definite integral taken with respect to y. And we measure these rectangles here, everybody, when they're running left to right, with right curve, which would be over here, minus left curve, which would now be over here. But remember, everything needs to be solved for x in terms of y. So what stops these rectangles on the right? That's the parabola, which is right here, already solved for x. So the right curve is going to be 9 minus y squared. Not a bad idea to put parentheses around that. And then minus. What stops those green rectangles on the left? That right here would be the line x equals 5. Okay, so that's what that one would look like. Limits of integration would need to be the lowest and highest values of y. So it would need to start right here and end at this spot right over here. So let's set these two equations equal to each other. I should say these two expressions equal to each other, and let's see where that gets us. 9 minus y squared has to equal 5. I'll bring the y squared to the right, the 5 to the left. 9 minus 5 is 4. That equals y squared. Square root on both sides. Y is plus or minus 2. Now, what I see here, guys, is if I look at this region vertically like this, there's some symmetry. I mentioned this earlier. So I would probably integrate this region from 0 to 2 and then double my answer right there. And I bring that up because, again, I don't think this one looks that bad. I think I want to try doing this by hand. 9 minus y squared minus 5. That's going to simplify just a little bit. So 2 times the integral from 0 to 2. The 9 minus 5 is going to be 4, and then a minus y squared dy. I don't think I can simplify that any further. I also don't think I need to, because from this spot, I think the antiderivative looks tolerable. 2 times, here we go, anti-differentiating 4 with respect to y is going to be a 4y, and then minus a 1/3 y cubed, got it, from 0 to 2. So we'll leave the 2 out in front. Let's put the 2 in there. 4 times 2 is going to be 8, minus 1/3 times 8 is going to be 8/3. That's what you get from the 2, minus, and now putting a 0 into a polynomial function is just going to get you a 0 as well. So what does that do for us, guys? Remember that this 8 is actually 24 over 3, so we have a common denominator right there. This becomes 2 multiplied by, 16/3, which is going to get us 32/3 square units for the area of that region if we integrated with respect to y. So The whole point of this problem was to help you guys recognize here that you can either get the same answer, the correct answer, either way, if you do it with respect to x or with respect to y. I personally think the method on the right was a little bit simpler, but I'll leave that up to you guys. You have the option of doing this one either way.